Right. Okay. So today we are going to discuss the unit test paper that we did for the atomic structure unit. So there are 50 MCQs. Let's quickly discuss these 50 questions. And if you have any doubts, let me know. And let's have a discussion about these questions, right? So today we are going to discuss unit test paper. Atomic structure. Let's go for the first question. MCQ number 1. Select the correct statement from the following. Gamma rays are negatively charged. What do you think? Students, I told you that when you compare the gamma, alpha, beta, gamma, so alpha rays means actually we can consider these helium nucleus, right? Helium nucleus. So these are positively charged, right? Helium 242 plus cation. So therefore, you can clearly see that this is positively charged, right? And beta means actually nothing else but electrons. So therefore, these are negatively charged. Negative charge. And remember, gamma rays are actually neutral. Neutral means they do not have any energy, any charge. So therefore, gamma rays are negatively charged. The first statement is wrong. Beta rays are positively charged. That is wrong. Beta rays are negatively charged because they are electrons. Alpha rays have opposite charge of beta rays. That's correct because alpha rays are positive charge and beta rays are negative charge. And it's charged twice the charge of beta rays. Is that correct? Remember, when you consider the charge of alpha particles, it's +2 because this is helium nucleus. And beta, we have -1 charge because that's an electron. Negatively charged -1, relative charge is -1. So here we can see that +2 charge is there. So quantitatively, when you compare the beta rays and alpha rays, we can consider that charge of alpha rays is equal to the twice the charge of beta rays. Twice the charge of beta rays, that's correct. So therefore, the statement that they have given, third one, is the correct answer. What about the fourth one? In a magnetic field, gamma rays are deflect perpendicular to the magnetic field. Remember, students, in a magnetic field or else in an electric field, gamma rays are actually moving without any deflection, without any deviation, directly in a straight line. These gamma rays are moving. So therefore, no deflection in the presence of magnetic field for the gamma rays because gamma rays are neutral. Fourth one is wrong. Result of the Rutherford's Goldfoil experiment could also be obtained by bombarding gamma rays on to a thin Goldfoil. That's wrong. Remember, alpha particle scattering experiment, right? If not Goldfoil experiment, is conducted by using alpha rays, alpha particles. Can you remember the diagram we learned? Source of alpha particles is used, and these alpha particles are going through a thin gold foil. So we know that when the atomic nucleus, when these alpha particles meet the atomic nucleus, they are deviating, right? The deflections will take place. So because of the same charge. So if the gamma rays are used, we can see that clearly gamma rays are going through the gold foil without any deflection. So then how we can find out the nucleus? We can tell that most of the space in the atom is empty. That's okay because gamma rays are easily going through the thin gold foil. But remember, we can't understand, we can't observe the concept of the nucleus if we use gamma rays. So therefore, it's not the correct idea that they have given. Bombarding gamma rays is not possible. Only we can use positively charged particles like alpha rays. So therefore, question number 1 answer is third. Question number 2. The correct statement regarding the substances nitride, oxide, and fluoride, N3 minus, O2 minus, and F minus fluoride. They all have the neons configuration 3s2, 3p6. Is that correct? Remember, when you consider these three species, they have given N3 minus, O2 minus, and F minus. Look at this one. This is N3 minus and O2 minus and F minus. They have actually 10 electrons, right? Atomic numbers are 7, 8, 9. So nitrogen has gained 3 electrons. So therefore, number of electrons are 10. For the oxygen also 10, fluorine also 10. So therefore, number of electrons are 10. So therefore, we can consider this is an isoelectronic series, right? We can consider this one as an isoelectronic series. What does mean by isoelectronic series? Isoelectronic series means the chemical substances which have the same number of electrons considered as an isoelectronic series. So therefore, N3 minus, O2 minus, F minus, since they have the same number of electrons, we can consider they are in an isoelectronic series, right? So they have the configuration. We know that this is actually neon's configuration. We can write down just neon's configuration. If not, if you want to write down the condensed electron configuration for this one, you can write down helium's configuration. This is 1s2, 2s2, 2p6, right? So this is the condensing electron configuration for the N3 minus, O2 minus, and F minus. So here they have given, they all have neon's configuration 3s2, 3p6. We know that neon's configuration 3s2, 3p6 means that is argon's configuration, right? Because neon containing 10 electrons, here 8. So therefore 18 electrons. So therefore 18 electrons means argon. So therefore this is not the correct condensed electron configuration for nitride, oxide, and fluoride. So this should be the correct one. Okay. So therefore the first statement is wrong. Nuclear charge ascend in the order F minus, O2 minus, N3 minus. Which one has the greatest nuclear charge? Fluorine. Because we know that atomic number is 9. Atomic number is representing the number of protons. Oxygen has 8. Nitrogen has 7. So therefore, fluoride has the greatest nuclear charge, right? So the next one should be O2 minus, and the next one should be, last one is N3 minus. So if I write down the ascending order for the nuclear charge, in this way. Nuclear charge. Nuclear charge is calculated by counting the number of protons, right? So here 7, 8, 9. So therefore the variation that they have given is wrong. Above species are not in isoelectronic. Wrong. This is actually isoelectronic, right? Just now I explained you because they have the same number of electrons. Their ionic radii ascend in the order F minus, O2 minus, N3 minus. Students, I told you that when you are asked to compare the radius, first of all, count the number of electrons. That is the most important thing. Now we have counted the electrons, the number of electrons in each species. We can see that is 10. So therefore, they are containing isoelectronic series, same number of electrons. Then we don't have to worry about the number of electrons. We have learned that there are two factors affecting to the atomic radius. What are they? In theories, we learned that atomic radius is depending on two factors. Atomic radius is depending on two factors. Number one, we can consider that is a nuclear charge. And the next one is shielding effect. Shielding effect. I taught you that when the nuclear charge decreases, atomic radius is increasing. That means atomic radius and nuclear charge, they are inversely proportional. And when you consider shielding effect, when the shielding effect increases, we can tell that atomic radius is increasing. So these are the two main factors affecting to the radius. So shielding effect means number of co-electrons. So we don't have to consider the shielding effect here because shielding effect is same. Number of co-electrons in these three species, 2, right? Except the valential electrons, the remaining are co-electrons. So co-electrons are 2. Therefore, you don't have to worry about the shielding effect here. Then the only affecting factor is nuclear charge. So nuclear charge can be calculated by counting the protons, right? Then protons, tell me how many protons are there? 7, 8, 9. And what is the relationship between the nuclear charge and radius? I told you that when the nuclear charge increases, atomic radius decreases. They are inversely proportional. Then tell me, students, how the atomic radius vary. So which one has the greatest radius, right? If the number of protons or else nuclear charge decreases, we can say that it has the greatest radius. N3 minus, nitride, has the greatest radius than oxide. Oxide has a greater radius than chloride. So ionic radius varying in this. Can you understand? So this is very simple. Huh? These questions are very easy. All of the things are the things that we learn. Then the statement they have given, is that correct? The ionic radii ascend in the order F minus, O2 minus, and 3 minus. That is correct. They have equal radii. No, they don't have actually equal radius, because if they want to have the same radius, we have to consider that electron and proton count same, right? So therefore, we can't consider that radius is equal. So therefore, question number 2, answer is fourth one. Question number 2, answer is fourth. Question number 3. What is the element with the highest number of unpaired electrons in the outermost d sub-energy level? Very easily. Students, in the theories also, I told you that specifically you have to remember the valence electron configuration of the d block, fourth period d block elements. What are the fourth period d block elements? Normally, typically, generally, we say that 3D elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So you have to remember the electron configuration of these 10 elements as a valence configuration. 1s2, 2s2, 2p6, those things are not necessary. At least you have to remember the valence configuration, right? When we especially go for the MCQ questions like this, if they have asked MCQ questions from the fourth period D block elements, you should be able to get the configuration directly, right? If it is manganese, you should be able to tell that 3d5 4s2. If it is copper, you should be able to tell that 3d10 4s1. If it is zinc, 3d10 4s2. Scandium, 3d1 4s2. So likewise, you should be able to remember the valence electron configuration, right? So shall we write it quickly? Valence electron configuration of fourth period D block elements, if not 3D elements. Look at this one. We have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. 22, 23, 24, 25, 26, 27, 28, 29, 30. Right? I put star marks on chromium and copper. Why? In theories, we learned that they have some arrangement in the configuration, right? In order to obtain the greater stability, chromium's configuration and copper's configurations are rearranged. So therefore, we can say that it has some kind of a specific electron configuration. Now let's write down the valence configuration. Scandium is 3d1, 4s2. Titanium is 3d2, 4s2. Vanadium is 3d3, 4s2. We are expecting that chromium should be 3d4, 4s2, but that is 3d5, 4s2. Manganese is 3d5, 4s2. 3d6, 4s2. 3d7, 4s2. Nickel 3d8, 4s2. Copper, we are expecting 3d9, 4s2, but configuration is rearranging into 3d10, 4s1. Zinc is 3d10, 4s2. Right? Remember, students, when you consider zinc, all the atomic orbitals are completely filled with the electrons. We know that the maximum number of electrons can contain in the d sub-energy level is 10. The maximum number of electrons can contain a sub-energy level is 2. So therefore, the zinc has a stable configuration because all the atomic orbitals are completely filled. So the elements they have given copper, zinc. Students, we can reject copper and zinc, right? They are asking what is the element with the highest number of unpaired electrons. Unpaired electrons means single electrons in the outermost d sub-energy level, right? So tell me, they have given zinc, copper, iron, cobalt, manganese. When you consider these three elements, now reject copper and zinc because d orbital is completely filled. So therefore, no unpaired electrons. 3d5, 3d6, 3d7. So the d orbitals are like this. In this way, we can see that manganese, iron, cobalt, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. You can see that manganese has 5 unpaired electrons, Iron has 4 unpaired electrons, cobalt has 3 unpaired electrons, so therefore answer is manganese, right? So therefore question number 3, answer should be 4. Very easy, okay? These things are theories that we learn. Okay, next question is related to the emission spectrum, question number 4. Let's see. Question number 4. Consider the following statements regarding the hydrogen emission spectrum. In the given diagram, they have given 3 statements. We have to check whether these 3 statements are correct or wrong. And in the right hand side, they have given a diagram with 2 electron transitions, A and B. One is belong to Lyman series and the other one belongs to Balmer series. So, okay, I'll draw the diagram that they have given. I'll draw the diagram they have given. So when you consider the diagram they have given, it's like this. There are 5 principal energy levels. N equal 1, N equal 2, N equal 3, N equal 4, and this is N equal 5. And they have given electron transition, capital A from here to here. And this is capital B from here to here. Right. Students, you can see that the capital A line, the capital A electron transition is exactly belong to Lyman series, because we have learned that in the hydrogen emission spectrum, all the electron transitions which are falling to the first principal energy level is considered as Lyman series, right? And B, you can see that the electron transition is actually ended up with second principal energy level. That means electrons which are falling to the second principal energy level, they belongs to Balmer series. And therefore, if I complete the diagram, I can complete this diagram like this. Look at this one. Look. I think we have to consider for this direction, right, from right to left, frequency and the energy increase. Because we know that the greatest frequency belongs to Lyman series, okay? Because the energy gap between the energy levels are increasing. Then the lambda wavelength decrease for that direction. Then here we can see that these are the electron transitions. This is the line with the greatest frequency and the energy. Look at the gap. By looking at the gap, you can tell that. I'm going to complete the diagram. Then the fourth line should be like this, okay? And then after this one, we have to go for the Balmer series. Balmer series, this is the first line we can obtain in this diagram. And next electron transition is from N equal 4 to 2, and the last one here 3 to 2, right? So therefore, you can see that capital A and capital B are consecutive lines, consecutive electron transitions in the hydrogen emission spectrum, spectral line diagram, energy level diagram, right? In the energy level diagram, capital A and capital B are consecutive. Consecutive means they are close to each other, right? One after the other. After capital A, the next electron transition belongs to definitely Balmer series, okay? Because this is the last line we can obtain in the Lyman series, N equal 2 to 1. Then we have to go for the Balmer series. Balmer series, you can see that from 5 to 2. So look at the statements. In the theories, I gave you this diagram for the both direction, okay? Where that frequency is increasing for this direction and for the other direction as well. Can you remember we drew 2 diagrams in the same page? Frequency of line capital A is equal to the frequency of line B. Students, that is wrong. Capital A line is actually Lyman. It has greatest energy level gap. So therefore the frequency is greater in capital A. Here they have given N equal 2 to 5. So therefore that is not equal. The location of the lines capital A and capital B are consecutive in a spectrum. Yeah, correct. Consecutive. Consecutive means one after the other. So you can see capital B after the electron transition capital A. Lyman, this is the last line in the Lyman series can obtain, and this is the first line in the Balmer series. A and B represent the electron transitions of 2 lines in two consecutive series. Are they in consecutive series? Yes, this is Lyman and this is Barman, right? We know that after Lyman series, the next one is Barman. B and C statements are correct. So therefore, the correct statements is only B and C. Question number 4, answer is second one. Question number 4, answer is second. The first statement is wrong. Frequency of capital A and capital B, they have given capital A and capital B frequencies are equal. So look at the energy gaps, right? So when you consider this energy gap, this is not equal to n equal 2 to 4, because we know that when we are going far away from the nucleus, energy level gaps are decreasing. So therefore, this energy gap n equal 1 to n equal 2 energy gap is greater than the energy gap between 2 and 5. So therefore, energy is directly proportional to the frequency. So therefore, the greatest frequency or the greatest energy belongs to the capital A line. So therefore, the first statement is wrong. Question number 5 is very easy, right? Which of the following correctly matches the discovery and the relevant scientist? Look at the first statement they have given. Charge of an electron is James Chadwick. Is that correct? Charge of an electron found by, is that James Chadwick? Charge of an electron actually found by, what is the name? Could you answer the chat box? Who found the charge of an electron? Charge of an electron? Yes, Millikan, right? Robert Millikan. So therefore, that is wrong. Second one, mass of an electron, Neil Bohr. Actually, Neil Bohr, Neil Bohr, he represents the energy level diagram. That means atomic model. He represent the energy level model of the atom. So he didn't contribute for the mass of an electron. So that is completely wrong. E over m, value of an electron, J.J. Thomson. Is that correct? Yeah, that's correct. E over m ratio found by J.J. Thomson. That's correct. Neutron, R.A. Millikan. No, that's wrong, right? So this is actually Robert Millikan. Neutron was found by James Chadwick. Isotopes, Eugene Goldstein. No, actually Eugene Goldstein, he found the proton. So therefore, question number 5, answer is third one. Very easy. Very, very easy. Question number 6. When moving across a period that does not belong to the D block in the periodic table, the element named capital A was found to have the highest fourth ionization energy. The group that capital A belongs to. Students, very easy. Can you remember after the discussion of the ionization energy, I gave you a summary. I told you to remember this one. Especially, you will get the questions from this one. Ionization energy, highest in which group, lowest in which group. And when you consider some consecutive ionization energies like I1, I2, I3, I4 in this way. Tell me, first ionization energy is greater in which group? When you draw the ionization energy graph, you know that the first ionization energy belongs to group number 18. Highest first ionization energy belongs to group number 18. And the lowest first ionization energy belongs to group number 1. Lowest first ionization energy. And when you go for the second ionization energy greatest in group number 1. and the lowest in group number 2. Third ionization energy, highest in group number 2, lowest in group number 13. Fourth ionization energy, highest in group number 13, lowest in group number 14. So you can see the pattern in this. I taught you this one, right? Highest in which group, lowest in which group for the consecutive ionization energies, right? So therefore, they are asking fourth ionization energy, highest in which group, right? Which group the fourth ionization energy is highest? Group number 13. Because students, now when you consider aluminium like elements, for example, aluminium is group number 13. Aluminium, we can write down the configuration 1s2, 2s2, 2p6, 3s2, 3p1, right? 13. So this is aluminium. So fourth ionization energy means we are going to remove the fourth electron. After removal of the third electron, we are going to remove the fourth electron. That is the fourth ionization energy. You can easily remove this one. And you can remove these two electrons also, doesn't matter, right? Because these electrons are in the same principal energy level, you can easily remove them. But after removal of these three electrons, can you see that you are going to shift to the second principal energy level? When you are skipping for this next principal energy level, you have to give a lot of energy because that energy level is very close to the atomic nucleus than the third principal energy level. So therefore, in order to remove the fourth electron, you have to give a lot of energy. Therefore, we consider that aluminium, boron like elements in the group number 13 have the greatest, highest fourth ionization energy, right? So therefore, we can consider question number 6 answer is third one. Question number 6 answer is third one. Let's move to the question number 7. The pair of periodic properties that shows the gradual increase and gradual decrease respectively across a given period in the periodic table, right? So look at this one. The first one they have given atomic radius and the first ionization energy. Students, we know that when we consider the radius, how that radius is varying along a period and across a period and along group. We know that from left to right, atomic radius is decreasing. Along a period, atomic radius is decreasing. So you can see gradual decrement there. Atomic radius decrease. Down to the group, what will happen to the atomic radius? Down to the group, atomic radius is increasing. Atomic radius increase down the group. Okay. So therefore, you have to understand here they have given gradual increase and gradual decrease. And they have given first ionization energy, second ionization energy also. Remember students, first ionization energy, second ionization energy doesn't have any gradual increment or gradual decrement, right? Now, for example, when you consider, they're asking along a period, right? Along a period, right? When you consider the second period elements, we know that the ionization energy varying in this way. Can you remember? This variation is known as zigzag variation. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So when you consider across a period, this is not the gradual increment, right? So this is considered as a zigzag variation, right? So therefore, we cannot see gradual increment or gradual decrement along a period for the first ionization energy or second ionization energy. So therefore, you can reject the answers number 1, number 5, number 4. Therefore, the answer is going between electronegativity and the atomic radius, right? atomic radius and the electronegativity. Remember, electronegativity, how that electronegativity is varying, especially when you consider the second period elements, right? You can see the pattern. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. I told you this one. Fluorine's electronegativity value is 4.0. Oxygen is 3.5, nitrogen is 3.0. Carbon is 2.5, boron is 2.0, 1.5, 1.0. So therefore, you can see that the gradual increment, right? So therefore, across a period from left to right, across a period from left to right, from left to right, electronegativity increasing. So therefore, you can see the gradual increment. So the radius is decreasing, electronegativity is increasing. So therefore, gradual increase can be seen in electronegativity, gradual decrease can be seen in atomic radius. So therefore, question number 7 answer is second one. Question number 7 answer is second one. Right? That's very easy. Question number 7 answer is second one. Correct your mistakes, identify your mistakes, what you have done in the examination time. So you should be able to go for the correct answers like this. Okay. Right. Now let's move for the question number 8. Question number 8 belongs to hydrogen emission spectrum. Again, what is the answer for this one? Assume that an electron of an hydrogen atom is excited to the fourth energy level in an experiment on the emission spectrum of hydrogen, right? That means there is an electron in the fourth principal energy level. Which of the following is correct regarding the electron transition? If the electron first moves from the fourth to second and then goes to the ground state, fourth to second and then second to 1, right? That means they have considered separate electron transitions, right? 4 to second, then second to 1, right? Let's see. Let's draw the diagram for this one. So we can see that these are the energy levels. Since they have given up to n equal 4, I will draw n equal 1 to n equal 4. So they have clearly mentioned that electron transition, first of all, from the n equal 4 to 2, then 2 to 1, right? Same electron, but there are two transitions, n equal 4 to 2 and then 2 to 1, right? That's how they have given. Then they're asking the H alpha and H beta lines are obtained. What do you think? Remember, this electron transition 2 to 1 belongs to Lyman series, right? So H alpha, H beta, H gamma, H delta, these lines are obtained in the Balmer series because Balmer series is actually partly visible. We can see 4 electron transitions. First 4 electron transitions in the Balmer series. So therefore, we are giving some names like H alpha, H beta, H gamma, and H delta. So when you consider Balmer series, so let me draw the 5th principal energy level also, 5 and 6 also. Please disregard the gap between the energy levels. If not, I will draw the correct diagram. Listen to this one. Let me take n equals 6, 5, 4, 3, 2. Okay. I have included many questions in the paper from the hydrogen emission spectrum. So therefore, you should be able to answer for these questions. This is n equal 2 to 1 transition, right? And as we discussed, this was the n equal 4 to 2 transition. These are the electron transitions that they have mentioned. Okay. Now, when you complete the Balmer series, the Balmer series should be like this. This is n equals 6 to 2, 5 to 2, right? In this way. Yeah. So this is H alpha, H beta, H gamma, H delta. We know that H alpha is red color, right? Revise the theories you learn. H beta, what is the color? Green color. H gamma, what is the color? Blue color. H delta, violet or purple color, right? So therefore, we consider Balmer series is partly visible. We can see these lines. So they have given H alpha and H beta lines are obtained, right? So these are only the two electron transitions you can see, the black color lines. So therefore, you can see H gamma, yes, H gamma electron transitions and the first electron transition n equal 2 to n equal 1 in the Lyman series. So you cannot see H alpha, H beta, wrong. Lines in the Balmer series are not obtained, wrong. N equal 4 to n equal 2 electron transition completely belongs to the Balmer series. So therefore, the Balmer series lines are not obtained. We can't accept that statement, wrong. Third one, H beta line and a line from the Lyman series is obtained. What do you think? H beta line. You can see that students, I made a mistake here actually. This is H alpha, okay? This is H alpha line. This is H beta, H gamma, and this is H delta. Okay. Now, okay, right. So remember, this is H alpha line. Okay. N equal 3 to n equal 2 is the H alpha. N equal 4 to n equal 2 is the H beta. Then 5 to 2 is H gamma. 6 to 2 is H delta. So therefore, you can observe H beta line only. That means a green color line. So H beta line and a line from the Lyman series. 2 to 1 is Lyman. So therefore, that's correct. So question number 8 answer is third one. But anyway, let's go for the other two statements also. Lines in the Lyman series are not obtained. Wrong. 2 to 1 transition is completely belong to Lyman series. The two lines that are obtained due to the electron transitions are the lines pertaining to the bracket series. We can't see any electron transition that belongs to bracket series. Why? Bracket series means Lyman, Balmer, Paschen, bracket. Bracket means electron transitions which are falling to the fourth principal element. Actually, the electron transition is starting from the fourth principal element. So therefore, this is not correct. Number 5 statement is wrong. Okay. So therefore, the correct one, question number 8, answer is third one. Question number 8, answer is third one. Question number 9. What is the number of orbitals containing unpaired electrons present in the last sub-energy level of an element whose valence electron configuration is 4s2 4p4? Very easy. Students, if the configuration is 4s2 4p4 valence configuration, We know that S sub-energy level is containing 1 orbital, P sub-energy level containing 3 orbitals. So here S sub-energy level is completely filled with the electrons in this way. In the P sub-energy level, we know that according to the Hund's rule, electrons are filling with the parallel speed 1, 2, 3, and the fourth electron is like this. So this is the way that electrons are filling to the atomic orbitals if the valence configuration is 4s2, 4p4. Now tell me how many unpaired electrons are there? 1, 2. So therefore, this question is very easy. Question number 9, answer is first one because there are 2 unpaired electrons. Question number 9, answer is first one. Right? Very easy. Many questions I have included in this paper. It's not difficult, no? Easy. I think easily you can score 35 MCQs. There are some difficult questions also, but scoring 35 MCQs, that means 70% of this paper is not that much of a big deal. Okay. And more than 80% is very good. Okay. If you do the paper honestly within 2 hours and you get more than 80% means very good. So the next unit test, unit number 2, unit number 3 will be somewhat complicated than this. Understood? Right, okay. Now students, let's go for the question number 10. 10 also very easy. Electron filling order of cobalt 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Remember students, here they have given the electron filling order of cobalt, right? So therefore, sometimes if you consider the electron filling order in order to go for the answers for this question, you might go for the wrong answer. So therefore, since they have given the electron filling order, let's write down the configuration. What we have to do? When we are writing the electron configuration, we have to arrange the atomic orbitals in the correct order. 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. Right? So the filling order is 4s2, 3d7, but the configuration is 3d7, 4s2. Then they have given cobalt is forming cobalt 2 plus cation. So when it is forming cobalt 2 plus cation, what is the configuration? 1s2, 2s2, 2p6, 3s2, 3p6. These 2 electrons are removed. Therefore, 3d7, 4s0. Right? So they have given this 3d7, 4s0 configuration in the fifth answer. Very easy. Question number 10, answer is number 5. Okay. Since they have given the filling order, if you consider the filling order, right, sometimes you might think that 3D, 4s2, 3d7 means, then the configuration is 4s2, 3d5. Then it is wrong. Right? Sometimes you might consider here, this is equal to what? 4s0, 3d7 in this way also. That is also wrong, right? We have to write down the correct electron configuration in the order and then remove the electrons, right? According to the correct order of the energy levels, 4s should come last. In this way, try to understand. Huh? So therefore, question number 10, answer is number 5. Next one. Question number 11. Which of the following correctly depicts the variation of the first ionization energy of sodium, magnesium, aluminium, silicon? Remember students, sodium, magnesium, aluminium, silicon. Magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So these elements belong to the group period number 3, right? So therefore, when we draw the ionization energy graph, they're asking about the ionization energy, right? Sodium has the least one. Then we can go for the magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Silicon, phosphorus, sulfur, chlorine, argon. So shall we write down the variation? of the ionization energy. We can see that sodium and magnesium, which one has the greatest ionization energy? Magnesium. Magnesium, aluminum, which one has the greatest one? Magnesium. Then aluminium, silicon, definitely silicon is greatest. Then phosphorus has the greatest one. Phosphorus, sulfur, again phosphorus has the greatest one. Then sulfur, chlorine, argon. So this is the variation of the first ionization energy, right? This is the variation of the first ionization energy for the third period elements. So they're asking about sodium, magnesium, aluminum, silicon. So in the which one, in the which part you can see the correct one? They're asking about sodium, magnesium, aluminum, silicon. This part. So this part can be seen in the first one, first option, first answer. Question number 11, answer is number 1. See how easy these things are. If you can remember the ionization energy graph, going for the answer is not that much of a big deal. You have to remember this variation. Okay. And finally, ultimately, I told you that how to compare the 20 elements, first 20 elements, you have to remember that variation also. Question number 11, answer is number 1. First ionization energy varying in this. Yeah, after completion of the unit number 2 and 3, I will keep a term test also. So that is actually named as term test. Yeah, because term test means general chemistry. Your first term test is actually should come from general chemistry. 1, 2, 3. So I will keep an exam from that one also. Okay. I won't keep any exam from the essays, structured essays, because you have to write down a lot of structured essay questions and essay questions. But I will keep the examinations from the unit number 2, unit number 3, and the first term test by only giving MCQs. Okay. Later we can do structured essays and essays. First of all, you have to have some practice of writing essays and structured essays. So that will be practiced by paper class. Soon after the third unit completed, I'm going to start the paper class also. Okay. Remember, students, how much you do the papers, right? So that will affect your examination. Keep that in your mind, right? Learning theories is not only enough factor. You have to do a lot of papers. I'm telling you this one again and again. Most of the students, many students don't understand this, right? At the end only, when the examination is getting close only, you will understand, I could have done some papers before from the earlier. So you will regret that one. So that's why we are starting the paper class earlier. Normally, we don't have to start the paper class in our time period when we are doing A level. Actually, our teachers started the paper class before 1 year. Now we have to start the paper class soon after 3 chapters finishes, because students need to practice a lot of questions, right? We have to do those things with them because you don't have time and you also not doing that one. So we have to do past paper discussion and everything, right? So in our classes, actually, they didn't discuss the past papers, all the past papers. Now we have to discuss all the past papers, right? So therefore, the trend is changed. So you have to do a lot of work. That's the thing. The only change is the examination is getting more competitive. Okay. So don't think that the papers are becoming easy. So they are trying to make the paper more competitive. Okay. But don't worry, you have opportunities. Right? So that means even after you getting some kind of a middle result means 1B, 2C, or 3B, sometimes for 3C passes, they have given opportunities in the universities, right? So therefore, I'm telling you to take 3 years, right? All of you must try for 3 years. But the sad truth is, not everyone is getting 3 years. That is the reality. So therefore, you have to try your maximum. Okay. So that's why I'm telling you that you have to do a lot of papers. How much the papers you will do, that much you will be prepared for the examination. Okay. Question number 12. What is the basis of the modern periodic table? Very easy. Electron configuration and the atomic number. So this is completely theory. This statement is given in the theory note. Question number 12. Answer is third one. Next one. Next one is a calculation. The wavelength of a yellow color is formed in a certain spectrum is 569 nanometers. The energy of 1 mole of photon of this wave. Right, okay. Let's write down the steps of this calculation. Under the electromagnetic radiations, we discuss about the energy of an electromagnetic radiation can be calculated using E equal h nu according to the Planck's theory. We know that students, Max Planck said that energy of a photon is directly proportional to the frequency, right? Nu is frequency. And the frequency, the proportionality symbol can be removed by adding a constant, that is Planck's constant h nu. And we know that we have equation C equal nu lambda. So when you subject here nu, C over lambda. So therefore, we can combine these two equations and form E equal hc over lambda. So E equal hc over lambda equation is giving energy of a photon. E equal hc over lambda is giving the energy of a photon, right? So when you find out here energy of a photon mole, you have to multiply this one by Avogadro number. So therefore, this is considered as energy of a photon mole. Energy of a photon mole. A mole of photon. Understood? So this is the difference between the two equations if you are finding the energy of a photon mole and photon. So here they are asking energy of 1 mole of photon. That means we have to use the second equation. Right? Okay, substitute for this one. E mole is equal to hc, capital L over lambda. Planck's constant is 6.626, 10 to the power minus 34 joule seconds. Velocity of light 3 into 10 to the power 8 meters per second. Avogadro number is 6.022, 10 to the power 23 per mole. Divided by lambda wavelength. They have given 569. So 569 nanometers means 10 to the power minus 9 meters. And we can write down this one in the correct scientific notation by 5.69, 10 to the power minus 7 meters. Look at how that units are cancelling off. Meters will cancel off. Per second, second will cancel off. So therefore, the remaining unit is joules per mole. Now, first of all, let me take these numerical values to the same place in this way. 10 to the power values will be 10 to the power 31, 38, 10 to the power 4 joules per mole. Since the unit they have given is kilojoules per mole, students, I can do like this. Look at this one. 6.626. Look at this one. Can you remember I told you that when we are doing the calculations, we can follow some trick like this. Avogadro number 6.022 and the Planck's constant, this value 6.626. This multiplication is equal to, what is the value that I told you? Can you remember that one? What is the value I told you? Avogadro number 6.022 multiplied by 6.626. This multiplication is equal to 39.9. Remember, 39.9. Right? 39.9 multiplied by 3 divided by 5.69. Okay? In this way. And we know that I can separate this one into 10 to the power 3 joules per mole. 10 to the power 3 joules means we can tell that is kilojoules, right? Then 39.9 multiplied by 30 divided by 5.69 is kilojoules per mole. Okay, now using logarithms, you can find out the value. use log values, logarithm, log table in order to go for the answers. Log value for 39.9, 39.9 is 6010. 1 point. Log value for 3 is 4771. So therefore 18710 3, 3.0781. Log value for 56.9. 56.9 is 7551. 0 point. So take the difference 0, 3, 2, 3 here, 2. 2.3230. 3230 antilog. 21, 0, 4. 2104 kilojoules per mole. 210.4 kilojoules per mole. So this answer is given in the fourth one. Yeah, question number 13. Answer is fourth one. Question number 13. Answer is fourth one. Right? So do the calculation correctly. So 10 to the power 4 or 10 to the minus 4. No, 10 to the power 4. Ne? So Atika, look at this one. Minus 7 will go for the numerator. Then plus 7, 10 to the power 8, 10 to the power 23, 10 to the power 7. This is minus 31. So then 7, 23, 30. 30 into 8 is 30. 38. Then here we have 10 to the power minus 34. So minus 34 plus 38. What is the answer? 10 to the power 4, ne? Plus 4. It's not minus 4, right? Understood? Okay. Complete the calculation. Right. Now let's move for the question number 14. Students, question number 14 related to the quantum numbers. They have asked a question like this. Possible set of quantum numbers for the unpaired electron in ground state copper atom could be. So what is the electron configuration of copper atom in its ground state? Copper 29, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. So therefore you can see that the only unpaired electron is this 4s1 electron, right? So that means we have to write down a possible quantum number set for this one. So what are the 4 types of quantum numbers we learned? The 4 types of quantum numbers: N, L, ML, MS. What does mean by N? N is principal quantum number. L means azimuthal quantum number. Principal quantum number is representing the principal energy level. Second one is azimuthal quantum number or angular momentum quantum number, which is representing the sub-energy level. ML is representing the magnetic quantum number, which is the atomic orbital time. MS is the spin quantum number, which is representing the rotation of the electron, whether it is plus half or minus half. So this is 4s1 electron, right? This is the only unpaired electron that we can see. So the 4s1 electron representing the fourth principal energy level are therefore 4, right? Principal quantum number is 4. What is the sub-energy level? Sub-energy level is S. I told you that under the angular momentum quantum numbers, S, the value that for the quantum number, angular momentum quantum number for the S sub-energy level is 0. For the P sub-energy level, that is 1. For the D sub-energy level, 2. F sub-energy level, 3 likewise. So therefore, this is 0. And the orbital that we have for the S sub-energy level is S orbital. Therefore, that is also 0. Spin quantum number, we don't know exactly the rotation. So therefore, it can be plus half, or else we can write down another possible quantum number set, 400 minus half. Both correct. Both of them are correct. So they have given, they have given this first quantum number set in the fifth answer. Others are wrong, right? First, second, third, fourth answers that they have given are completely wrong. Question number 14 answer is number 5. So that question related to the quantum numbers. Right, okay. Now let's move to the next question. So the next question is also a calculation. Read the question carefully. A sodium vapor lamp emits yellow color in the visible light. Wavelength is 582 nanometers. The lamp generates energy of 8 joules per second. Number of photons generated by the lamp within 66.26 seconds. Right. So there is a sodium lamp and it is working for 66.26 seconds. And the energy that is generated by this lamp per second is 8 joules. So you can find out the total energy emitted by this lamp, right? Students, look at this one, how to do this calculation. They have given energy per second is 8 joules per second. And the time taken is 66.26 seconds. Then you can calculate here the total energy. When you multiply this energy 8 joules per second, 66.26 seconds. Then you can obtain the total energy. I'll keep this one without simplifying. 8 into 66.26 joules. So this is the total energy. This is the total energy emitted by that sodium vapor lamp. Now we can calculate what is the energy of a photon. Energy of a photon can be calculated E equal hc over lambda. Planck's constant 6.626 multiplied by 10 to the power minus 34 joules second. Velocity of light 308 meters per second divided by lambda wavelength is given 5.82 10 to the power minus 7 meters. Right? So therefore, here we can see second per second will cancel off, meters will cancel off. Energy of a photon will be 6.626 multiplied by 3 divided by 5.82. Then the answer 10 to the power. So 15, 34, 15 here answer will be 19, minus 19 joules. Right? If you want, you can simplify this one because this is divisible by 3. So here 1, 28 means we can say that 9, 4, 1.94. Then the energy of a photon is equal to 6.626 divided by 1.94, 10 to the power minus 19 joules, right? According to the wavelength that they have given of the yellow color wavelength, this is the energy of the yellow color light. This is the energy of a photon of the yellow color light. And this is the total energy emitted by that vapor lamp. Then, if this is the energy of just one photon, if this is the total energy, when you divide the total energy by the energy of a photon, you will obtain the number of photons, right? Look at this one. Now, students, you can see that this is the energy of a photon, right? Let me write down here in this way. This is the energy of a photon. And this is the total energy emitted by that lamp. In order to calculate the total number of photons, this is equal to total energy divided by energy of a photon. So the total energy is 8 into 66.26 joules. What is the energy of a photon? 6.626 divided by 1.94, 10 to the power minus 19 joules. Joules cancel off. Unitless, yeah, because number of photons should be unitless. And can you notice that me 6.626, 66.26, right? So only the decimal values are changing. 1 here, 10 here. Then 80, 1.94 will go for the numerator, 10 to the power 20. 1.94 into 8, 10 to the power 21, right? So 1.94 into 8. What is the multiplication? 32, 3 here. 7 here, sorry. Then we have the answer 15.52, 10 to the power 21. Did I do the calculations correctly? Yeah, this is 10 to the power 19. Okay. Then this becomes 20. 20, yes. And then 1.55 to 10 to the power 21 photons. This is the answer. So this answer is given in the second one. Question number 15, answer is second. Right? So you have to do this calculation very carefully. Question number 15, answer is second one. Quickly complete this one. right? Okay. Okay. So students, next one, question number 16. Question number 16. The response which correctly represent the order of decreasing energy of following quantum number set, right? Students, this is actually related to the quantum numbers again, but the energy of orbitals, energy diagram that I taught you, so that is also important here. Let's see how to go for the answer for this kind of a question. So here we can see that simply n equal 4, L equal 0, ML equal 0, MS equal plus half. Then simple B, n equal 3, L equal 1, ML equal 1, MS equal minus half. And C here, n equal 3, L equal 2, ML equal 0, MS equal plus half. D, n equal 3, L equal 0, ML equal 0, MS equal minus half. So these are the quantum number set that they have. Students, you have to understand this is fourth principal energy level. L equals 0 means S sub energy level. So therefore, this is 4s orbital, isn't it? This is third principal energy level. L equal 1 means P sub energy level. So therefore, this is 3P. Then you have to understand this is N equal 3, third principal energy level. L equal 2 means D sub energy level. Then this is 3D. This is N equal 3, third principal energy level. L equal 0, S sub energy level. Then this is 3s. 4s, 3p, 3d, 3s. So these are the atomic orbitals. So now what we have to do, we have to arrange these things in the correct order of the energy. So in the energy diagram, we learned that the greatest, first of all, let's go with the lowest energy. So the lowest energy belongs to simple D. And the next energy belongs to simple B. And we can say that 3s, we have 3s, then we have 3p. And the next one, what is the next one? So the next one should be 4s, and the greatest energy belongs to C. So CABD. So this variation for this direction, energy increasing. So C is 3D energy, 4s energy, this is 3p energy, and this is 3s energy. Okay. So therefore, you can say that the correct variation should be CABD, third one. Question number 16, answer is third one. So question number 12, answer was third one, Rohidarshan. C is greater because 3D energy, right? Third principal energy level, d orbital is the greatest energy. According to the Aufbau principle, we can say that the greatest energy, electrons are filling to the 3D before, electrons are filling to the 4s before 3D. So therefore, when the electrons are filling to the orbitals, always they are filling to the orbitals with the lowest energy. So therefore, 4s has the lowest energy than 3D. So therefore, 3D has the greatest energy. Right. Question number 17. A, B, C are three elements with only one unpaired electron, which belongs to the fourth period. Okay, that means they have given only one unpaired electron in that element. Unpaired electron in capital A and capital C can have the same principal quantum number, same azimuthal quantum number, same magnetic quantum number values, and same or opposing ms values. That means spin quantum number can be changed, plus half or minus half, but other three quantum numbers are same for the capital A and capital C elements. Unpaired electron of capital B can have 10 set of quantum numbers. 10 set of quantum numbers means definitely that unpaired electron is actually belongs to the D block. Let's see. Yeah, elements A, B, C can be respectively. Right. Okay, students, first of all, tell me what are the fourth period elements? The fourth period is starting from which element? Period number 4 starting from which element? Period number 4 is starting from potassium. So we have potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Then we have gallium, germanium. What is the next one? Gallium, germanium, arsenic, selenium, bromine, krypton. Am I correct? Are these the fourth period elements? Gallium, germanium, arsenic, selenium, bromine. So these are the fourth period elements that we can write down. So they have given unpaired electron in capital A, capital C have the same NLM values. A and C have the same NLM values. Unpaired by electron of B have 10 set of quantum numbers. Remember, students, they have given what are the, according to the given answers, given options, right? Let me write down the options also. Potassium. So this is A, this is B, this is C. Potassium, option number 1, scandium and copper. Option 2, potassium, gallium, scandium. Option 3, potassium, copper, gallium. Option number 4, scandium, copper, gallium. Option number 5, potassium, copper, gallium. So these are the three options they have given. So only D block element that they have given, right? What are the D blocks? So this is the D block elements, scandium to zinc. Only the element they have given is what? Copper, right? You know that potassium belongs to S block, right? So therefore the unpaired electrons. So calcium we can't take because calcium has the configuration S2 and this is S1, right? So therefore we can see that potassium can be taken as an unpaired electron, but calcium we can't take, right? So therefore potassium is given. Potassium is actually S block and gallium is P block. Then we have given scandium and copper. So these are the elements they have given. In the scandium, we can tell that again, the configuration is 3D14S2. Since they have given copper, copper is also having 3D10-4S1 configuration. 3D10-4S1 configuration. But remember, students, they have given, look at this one, unpaired electron of B have the 10 set of quantum numbers. So definitely you know that this should be D block elements. And the only two D block elements they have given is scandium and copper. Then tell me, students, that unpaired electron is located where? In copper, the unpaired electron is belong to S sub energy level. Can we have 10 set of quantum numbers for that one? Right? We discuss about the copper's possible quantum number set for the unpaired electron. 400 plus half, 400 minus half. That's all. So therefore, we can't consider copper as the capital B element. Definitely that capital B element should be what? Scandium, because we know that 3D14S2, D sub energy level is containing 1 electron. There are 10 possible set of quantum numbers since there are 5D orbitals. We don't know exactly what is that possible quantum number set. Therefore, definitely you have to choose the answer. Just by reading the second statement, you can go for the answer as number 1. Right? But remember, let's check the other statements also. They have given at the beginning, capital A and capital C have same capital N value, simple N value, principal quantum number, azimuthal quantum number, and the magnetic quantum number. Same principal quantum number, same angular momentum quantum number, same magnetic quantum number for capital A and capital C. Now take potassium and copper. You know, students, potassium configuration is 1 is to 2 is to 2p6, 3 is to 3p6, 4 is 1 valence configuration. Copper valence configuration 4 is 1. So both the unpaired electrons in potassium and copper will have the same principal energy level, same sub energy level S, same orbital S. Only the difference is spin quantum number. That can be plus half or minus half, and this one can be plus half or minus. So therefore, the elements that we can take for capital A and capital C are potassium and copper. Because their unpaired electron belongs to 4s1. 4s1, this is also 4s1. So principal quantum number, azimuthal quantum number, magnetic quantum number, all three are same. Only the difference can be in the spin quantum number, right? Sometimes both of them can be same, right? So capital B should be definitely scandium, because scandium 3d1 unpaired electron belong to the d sub energy level. So therefore we can take any set of quantum numbers. Possible 10 set of quantum numbers are there. We can take one of them according to the given statements. Question number 17 answer should be number 1. So that is kind of a very good question, logical question in this paper. Right, okay. Now let's go for the question number 18. Consider the following nuclear reaction. So they have given a nuclear reaction. You have to complete this one. Students, this is very easy. Okay. So this is very easy. According to this reaction, nitrogen 714, this is alpha 24, and this is capital X element, and this is neutron 0 to 1, 0, 1. And we have to fill these two numbers. I told you that when we are balancing a nuclear reaction, what we have to consider is take the summation of the atomic numbers they have given in the left hand side, and you have to equalize that one for the right hand side summation of atomic numbers. So therefore here we have 0. This summation is 9, right? 9. So therefore we have to put here 9. And this summation 4 and 14 summation is 18. So therefore we have 1 here, and this is 17. So 917, fluorine 917 isotope, right? Atomic number 9 is actually fluorine. Fluorine 97 isotope can be seen in the third one. Question number 18, answer is third one. That's very easy. Right, okay. Let's go for the question number 19. That is isotopes, right? Yeah, abundance, relative abundance, that value. So bromine has two isotopes and average relative atomic mass of bromine is 79.91. Mass of bromine 81 isotope. Okay, they have given two isotopes of bromine 79 and 81, and they have given the masses also. Mass of one isotope bromine 79, relative abundance is given 50.54, right? Let's see how to do this calculation. So students, they have given an isotope bromine 79 and this is bromine 81. Mass of bromine is also given. This is 78.918 and this is, we don't know, relative abundance. They have given this is 50.54. Then we can tell the other one. You have to subtract this one from 100 and give the answer. 6 here, 164 and 9 4. 49.46. So this is the relative abundance value. Then average relative atomic mass is equal to, multiply this mass value 78.918 from the relative abundance 50.54 plus, and we don't know what is the mass of bromine 81 isotope. Let me take that one as x into 49.46 divided by 100. They have given this is equal to 79.91 in this way. X into 49.46 divided by 100. And when you shift this 100 to the left hand side, answer will be 7,991. And here we have 78.981, 50.54, x into 49.46. Okay, now you have to get the multiplication of this one. So doesn't matter, I'll use the logarithms quickly. So this is 7892. If you round off that one for the second decimal point, 7892. 7892 quickly. 92 is 8972, 1 point. Log value for 50.54. 50.54, 3, therefore 7036. Summation is 8, 10, 1, 3. So antilog of 6008. 6008 antilog. 3988. Therefore here we have 3988, 7991, and this is x into 49.46. When you get the difference of these two, 3988, difference is 3004. 4003. Then x equal 4003 divided by 49.46. So 4003 log value 4003. 4003 is 6024. 3 point. Log value for 4946. 4946 is 6946. 1 point. Difference to 8 here, 0, 0, 2. If I'm correct. 90, 82 antilog. 80, 9, 4. 80.94 is the mass. Have they given this kind of answer? 80.94. What is the approximate answer for this one? So the approximate answer for this one is 80.94, third one. Right? Third one. Question number 19, answer is third one. Remember, students, this is a calculation, okay? Approximate answer 19 is third one. Quickly do the calculations. You should be you should be able to handle with logarithms. Huh? That is also a good skill, mathematical skill, especially when we are doing the chemical calculations. In the examination, they are giving the logbook. Okay, don't worry. Right. Okay. Next question. Question number 20. Effective nuclear charge fell by valence electron of sodium. Right. Students, what does mean by the effective nuclear charge? Effective nuclear charge is a combination of two properties. Those are depending on those are affecting to the atomic radius. Effective nuclear charge. So effective nuclear charge is equal to, so this is denoted by Z, EFF. This is equal to nuclear charge. Nuclear charge minus shielding effect. So nuclear charge is C, shielding effect is S. So therefore ZFF is equal to Z minus S. So this is the equation that we learned. Remember, this is combination of the two factors affecting to the atomic radius, nuclear charge, right? We discussed that nuclear charge is inversely proportional to the atomic radius, while shielding effect is directly proportional to the atomic radius. Then how that effective nuclear charge is affecting? Effective nuclear charge is also inversely proportional to the atomic radius. Effective nuclear charge is also inversely proportional to the atomic radius. So therefore, we can say that atomic radius is inversely proportional to the effective nuclear charge, CFF. When effective nuclear charge decreases, atomic radius is increasing. Okay, so keep that in your mind. So now for the sodium atom, what is the effective nuclear charge for sodium? ZFF for sodium. Nuclear charge, sodium we know that 11 atomic number, so therefore there are 11 protons. What is the shielding effect? Remember students, nuclear charge can be calculated by counting number of protons. Then shielding effect can be found by counting the co-electrons. So the co-electrons means except valence shell electrons, others are co-electrons. In sodium, 1s2, 2s2, 2p6, 3s1. So therefore co-electrons are 10. Then here 11 minus 10 is. So effective nuclear charge fell by valence electron in sodium equals to +1. Question number 20, ours is second one. Question number 20, answer is second one. Quickly. These things are very easy, okay? Effective nuclear charge is not always equal to the valency, because we can consider that now. When you consider chlorine, chlorine's effective nuclear charge is, you know, the configuration is 1s to 2s to 2p6, 3s to 3p5. So therefore 17 minus 10. So the effective nuclear charge of chlorine is 7 plus 7. But what is the valency of chlorine? Chlorine is 1. Valency of chlorine is 1. So therefore, Fashan, we can't tell that valency and the effective nuclear charge all the time same. Okay. So you can't make a connection between the valency and the effective nuclear charge. Okay. All the time. Right. Okay. Next question. Question number 21. Correct regarding both calcium 2 plus and zinc 2 plus. So what is the statement correct regarding calcium 2 plus and zinc 2 plus here? Let's see. This is calcium 2 plus and this is zinc 2 plus. What are the first statement they have given? Same nuclear charge. So when you consider the nuclear charge means number of protons. So the nuclear charge for calcium is +20. So the zinc is +30. Equal? No, they are not equal. equal number of protons. So proton count is also same as the nuclear charge. So 20 and 30. Same number of electrons are in the outermost energy level, right? Electrons in outermost energy level, in calcium 2 plus. So calcium 2 plus is now like argon, right? So therefore, in the valence shell, there are 8 electrons. What about zinc 2 plus? Zinc 2 plus configuration is becoming 3d10 4s2. After removal of this 4s2 electron, we have 3p6 also, and 3s2 is also there. So therefore, number of electrons will be 18, outermost energy level. Same unpaired electrons in the outermost shell, right? Number of unpaired electrons. Number of unpaired electrons actually 0 for both of them. Number of unpaired in outermost energy level, both are having 0, right? None of them have the unpaired electrons. Has noble gas configuration? Yeah, calcium 2 plus has the noble gas configuration, which is argon. But zinc 2 plus, does it have the noble gas configuration? No, zinc 2 plus doesn't have any noble gas configuration. So therefore, the correct answer, right? Number of unpaired electrons in the outermost shell, both are same. So therefore, option, question number 21, answer is fourth one. Right, okay. So we were discussing about question number 20, 21, right? So now let's go for the question number 22. Question number 21, answer is fourth one. Now let's go for the question number 22. Which of the following correctly represent the variation of ionic radii? So therefore, the statement species they have given is N3 minus, O2 minus, F minus, sodium plus, Mg2 plus. I told you that, students, when you are comparing the radius, the main thing you have to do is count the number of electrons. 10, 10, 10, 10 for each. Nitride is 10, oxide is 10, fluoride is 10, sodium plus is 10, and magnesium 2 plus is 10. So therefore, we don't have to worry about the shielding effect. Shielding effect is same. Then you have to worry about the nuclear charge. So when you count the nuclear charge, so the nuclear charge will be, that means number of protons, 7, 8, 9, and here 10, 7, 8, 9, 11, 12. Okay, so then you can understand, students, they have same number of electrons. That means these species actually in an isoelectronic series. So in order to compare the radius, the affecting factor is number of protons. That means nuclear charge. Greater the nuclear charge, lower the radius. Then you can tell that the least radius belong to magnesium 2 plus. Then we have sodium plus. So F minus, O2 minus, the greatest radius belong to N3 minus. So this variation is given in the option number 5. Question number 22, answer is number 5. Very easy. Okay. Question number 22, answer is number 5. In question number 23, they have given 2 consecutive elements in the periodic table, and X is an noble gas. That means X is actually group 18 elements. They have given 3 properties, atomic properties, for this capital X and capital Y element. They have given 2 atomic properties of capital X and capital Y, 2 elements. XY, the variation is should be like this. And the second property, is like this. And the third property like this. Okay, in this way. So they're asking, what is this property? They have given three options: atomic radius, atomic radius. So the next option is first ionization energy, first ionization energy, and third property is electronegativity. Electronegativity. Students, try to understand. They have clearly mentioned this capital X is a noble gas. If it is a noble gas, we can consider that capital Y element should belongs to which group? Consecutive elements. That means one after the other. So if capital X is a noble gas, we can tell that belongs to group number 18. Then capital Y should go for the next period. That means group number 1, right? For example, neon sodium, argon potassium, helium lithium. After capital X grew noble gas, definitely we have group number 1 in it. Now, when you analyze these three graphs for the radius, first ionization energy, electronegativity, we know that capital X is a noble gas. Now, for example, just consider neon. After neon, we are going to go for the third period, which is group number 1, sodium. Then what will happen to the radius suddenly when you are moving from X to Y? When you are moving from X to Y, suddenly atomic radius is increasing. The reason is a principal energy level is increasing. Neon's configuration is 1s to 2s to 2p2 and 2p 2p6. Sodium's configuration is 1s to 2s to 2p6 3s1. That means third principal energy level is increasing. One ring is increasing, so therefore radius is suddenly increasing. So you can see that sudden increase is actually can be seen in here, right? So you can consider this one also, but okay, let's keep this one. Okay, this one, no, this one, but probably this can be the radius variation. What about this one? X has a greater property and Y has the less property of it. What about the first ionization energy? Can you remember when you draw the first ionization energy graph? Here we have neon and here we have sodium, magnesium, aluminium, silicon likewise continue. So from neon to sodium, first ionization energy decreasing. Therefore, definitely this is first ionization energy, right? No doubt about it. This is first ionization energy. And then this one, what about this one? So remember, this is actually not that much of large increment. So we can consider this one as the electronegativity. And the next thing is capital X is a noble gas. Sometimes we consider that for the noble gas elements, since they are not forming chemical bonds, its electronegativity is 0. But according to the Pauling scale, students, electronegativity values are there for the group number 18 elements also. They have some electronegativity values. But generally, we can say that since it is not forming chemical bonds, electronegativity is 0 because they have given this point is lying on the 0 value. So why we can't consider this one as the electronegativity? Then this is electronegativity. This property is the electronegativity. And the first one is atomic radius. And the second option is ionization energy. So therefore, this variation is like this. Question number 23. This option, atomic radius, quasar energy, and the electronegativity is given in the number 1. Question number 23. Answer is number 1. Right. Now let's move for the question number 24. Students, question number 24 is related to the ionization energy again. So look at this only. First of all, let me draw the ionization energy from neon. Here we have, just imagine, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, in this way. I will put the group number, then you will understand this one more. Group number 18, group number 17. This is group number 1, group number 2, group number 13, 14, group number 15, 16, 17. Then you will understand this one more. So they have given a graph, right? We have to find out these two elements, capital A and capital B, belongs to which group according to the ionization energy values they have given. They have given this kind of ionization energy values in this way. And this is A and B, first ionization energy. And this is the second ionization energy. Okay. Now look at the variation. So A to B, right? This kind of a variation can be seen in the first option, group number 17 to 18. 17 and 18. Where is 17 and 18? This is 17 and 18. So is that this variation? No. Therefore reject. First option is rejected. Group number 16 to 17. 16 to 17 also this kind of a variation, right? No, that is not applicable. Then group number 1 and 2. 1 and 2 also this kind of a variation. So therefore we should have this kind of a variation, right? For this direction. What about group number 18 and 1? This is okay. Ne? 18 to 1, we can see that decrement from A to B decrement. Yeah, so therefore answer can be fourth one, but let's keep that one. We go for the fifth one, 14 and 15. So 14 and 15 also like this. Then students, by looking at the first ionization energy, this variation, the decrement variation between two elements can be seen in group number 18 and group number 1. That is the answer. If you want, you can confirm it by considering the second ionization energy. Why? When you consider second ionization energy, these groups are going like this. First group element is going for here when we consider the second ionization energy. That means this becomes group number 1, right? And this becomes group number 18 for the second ionization energy. So therefore, then second ionization energy variation for group number 18 and group number 1 can be seen like this. For the group number 18 and 1, first ionization energy can be seen in this. So therefore, the correct option for this one, question number 24, answer is fourth one, right? That's a very good question, right? Question number 24, answer is fourth one. Right, okay. Question number 25. Select the element shows the positive electron gain energy. Remember students, in the periodic table we are discussing, there are three specific elements which can show the positive electron gain energies: beryllium, magnesium, and nitrogen. Keep that in your mind. These three elements have positive value for the electron gain energy, right? These three elements have positive electron gain energies. We know that electron gain energy means energy related by gaining energy. So that energy, if it is positive, we consider that is endothermic. That means it is absorbing the energy from outside. If it is negative, we consider it releases energy to outside, exothermic. So therefore, beryllium, magnesium, nitrogen, these three elements have positive electron gain energies. What is the reason? So the reason behind it is they have somewhat stable configuration. Beryllium, magnesium belongs to group number 2, therefore S2 configuration is there. Nitrogen belongs to group number 15, S2P3, somewhat stable. So because of these somewhat stable configurations, they have positive electron gain energy. So from the given options, question number 25, answer is third one. Question number 25, answer is third one. Question number 26, which is not true regarding the modern periodic table. Majority of the elements present in the periodic table are metals. Yeah, that's correct. I told you that 80% of the elements in the periodic table are metals. Number 2, among the elements of the P block, they exist in the elements belong to the elements belong to 3 states of solid, liquid, and gases. Yeah, that's also correct, because in the group number 17, we can see that. Can you remember, students? I told you that fluorine, bromine, iodine, and astatine. When you consider these 5 elements in group number 17 belongs to the P block. So fluorine is a gas. Chlorine also a gas. Bromine is a liquid. Iodine solid. And astatine is also solid. Specialty of this one is radioactive, right? So therefore, all 3 states of matter in the state exist in group number P block. That's correct. The modern periodic table is prepared based on the atomic number. Yeah, correct. That's also correct. So nuclei of the all elements of the periodic table have protons and neutrons. Is that correct? Nuclei of all the elements of the periodic table have protons and neutrons. Can you remember hydrogen? I told you that hydrogen doesn't have any neutron. At least one neutron? No. Hydrogen is just containing what? One electron, one proton. So therefore, that's wrong. I think this is the answer, because they're asking the incorrect statement, right? Which is not true. Within first 6 periods of the periodic table, there are 11 elements which exist in the gaseous state at the room temperature. Yeah, that's correct, right? So when you consider the gases in the periodic table, so what are the gases in the periodic table? Let's go period wise. So when you consider first period, second one, third one, fourth one, fifth one, and the sixth one, let's see what are the gases in each period. In the first period, we have hydrogen and helium. All the elements in the first period are gases. Second, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. There are 4 elements, 4 gaseous state elements. Third, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. And then after argon, we have krypton, xenon, radon. So this radon is actually belongs to 6th period. So therefore, we can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 gases are there in the periodic table. And you can see that, you can notice that the highest number of gaseous elements belongs to the period number 2. So we can notice that one also. So within first 6 periods of the periodic table, there are 11 elements which exist in gaseous state at the room temperature. That's correct. So therefore, the incorrect statement is fourth one. Question number 26, answer is fourth one. Question number 26, answer is fourth one. So the next one is very easy, students. The variation of the atomic radius and the first ionized energy and electronegatividity across a period, left to right, and the down the group in the periodic table is correctly given by. Right. Tell me, just now we learned that atomic radius. Atomic radius, how that atomic radius is varying along the period, decreasing, right? From left to right, it is decreasing. Down the group, atomic radius is increasing. First ionization energy, we don't have any gradual increment or gradual decrement along the period. But down the group, we can see that first energy is decreasing. What about the electronegativity? Electronegativity, down the group electronegativity is decreasing, along a period electronegativity is increasing. So we can see that the correct options that they have given. First one, atomic radius down the group increasing, wrong. Other that's correct. Down the group it is increasing. Across the period left to right increasing, that's wrong. First ionization energy down the group increases, wrong. Decreasing. Electronegativity down the group increase, no students, it is decreasing. Okay, across the period increasing, okay, that's okay, fine. Fourth one, atomic radius down the group increase, across a period left to right decreasing. Yes, fourth one is the option. First ionization in energy down the group decrease, across a period left to right normal increase, not normal increase, it's actually zigzag variation, right? We can't say that that is a normal increment. Okay, so therefore question number 27 answer is fourth one. Right. In the question number 28, they have given a table. I will quickly draw this table because by analyzing this table only, we have to go for the answers. They have given consecutive ionization energies for 4 elements, A, B, C, D. For capital A, ionization energy I1 2100, 3950, 6150 in this way. For capital B, 490, 4560, 6950. For capital C element, 736, 1450, 7750, 10,500. For capital D element, 575, 1800, 2740, and 11,600. So students, I1, I2, I3, I4 consecutive ionization energies. Analyze this table very carefully. Yeah? Now you can see that between the consecutive ionization energies of capital A, we don't see any sudden increment, right? We don't see any large energy gaps. But when you go for the capital B, did you notice that I have mentioned this one in blue color and black color? So you can see a sudden gap, sudden energy gap between these two values. 490, 4560. Can you understand? That means from here to here, you can say that we are shifting to another principal energy level, new principal energy level. Now analyze capital C. From here to here, suddenly you can see an energy increment. That means from here to here, you are going to shift to another principal energy level. And here, when you analyze this one, you can see that this is 2714, 40, this is 11,600. Look at the energy gap. then we are shifting to another large energy gap. By looking at these three, you can decide which group that element belongs to. Remember, students, there is an element which has the first ionization energy is very low and the second ionization energy is very great value compared to the first one. So what can be that one? For example, lithium, sodium, potassium, 1s2, 2s1, 1s2, 2s2, 2p6, 3s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. After removal of this electron, we can easily remove this electron. But when you go for the second electron that you are going to remove, we have to give a lot of energy. Neither. Therefore, we can say that this capital B belongs to group number 1. Right? You can confirm this is group number 2. Why? You can easily remove first electron and second electron. When you go for the third electron, you have to give a lot of energy. So the third ionization energy greater in group number 2 elements. Therefore, this is group number 2. Group 2. Right? Go for the next one. When you are trying to remove the fourth electron, you have to give a lot of energy. Then this is group number 13. These are consecutive elements. Then tell me what is capital A? Capital A is group number 18. So therefore, according to the given options, according to the given options, we can say that this is 18, group number 18, group number 1, group number 2, and group number 13. But I have an issue like this, students. The issue is the first ionization energy of group number 18 should be greater. Okay. Compared to these three elements, this one has a great ionization energy. So therefore doesn't matter. Okay. Compared to these three values, I1, first ionization energy of group number 18 is greater. Therefore that's okay. Right. So group number 18, 1, 2, 3, that's correct. So question number 28, answer is second. Okay. So that's also a good question, right? You have to analyze these things very carefully. Quickly complete that. Question number 29. The processes shown by the following reactions are mentioned correctly. Okay, students, they have given three processes. Let's see what are the processes they have given. X gas forming X plus gas by removing one electron. Students, you know this one. What is this? First ionization energy. This is first ionization energy, corresponding reaction. Next one, Y gas taking one electron to form Y minus gas. Then what is this? Electron gain energy. This is electron gain energy. electron gain energy. And here we have Z minus gas converting into Z gas plus electron. What is this? This is the opposite of the electron gain energy. That means electron affinity. Electron affinity. Right? Electron affinity. Opposite of the electron gain energy, right? So when you consider opposite of the electron gain energy, you will have electron affinity. So therefore, these three options are correctly given in the electron gain energy is B. So this is B, and this is C. First energy is A. Electron gain energy is B. Ionization energy is A. That is. So option is question number 29 asks second one. Question number 29 answers second. Question number 30. The atomic number of selenium is 34. The correct orbital diagram of electrons which are present in the valence shell. Right, okay. So we can say that selenium is 34. Electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p4, 10, 20, 30, 34. So up to here, all the orbitals are completely filled with the electrons. So therefore, 4p4, last valence shell, 1, 2, 3, 4. You can see that two unpaired electrons are there. So this orbital diagram, so they have given 4s2 also. This orbital diagram can be seen in the fifth one, question number 30, answer is number 5. Question number 30, answer is number 5. Okay. Right. So now we have completed 30 questions. Now we have to go for the last 20 questions, statement type of questions. Let's see. Quickly complete this one. Right, okay. Now let's go for the question number 31. Which of the following can show a tendency to form diatomic molecule? Students, diatomic molecule. Diatomic molecules are chlorine, Cl2, N2, O2, hydrogen, H2. So those are the diatomic molecules. So here they have given 4 options: chlorine, magnesium, neon, and sodium. Students, you can directly reject neon because neon is not forming any chemical bonds. It's not connecting to any atom. So therefore it is stable. It's not forming any bonds. So therefore you can reject directly neon. We can reject magnesium also because magnesium has somewhat stable configuration S2. So therefore we can consider that magnesium is not forming diatomic molecules, Mg twice. Sodium also, when you consider the electron configuration, it cannot form chemical bonds, diatomic molecules. But remember, when it meets another sodium atom, with the same configuration, this S1 electron and the other S1 electron can be connected. In the theories, I told you that at 400 degrees Celsius, sodium is forming sodium diatomic molecule, Na2. Understood? So therefore, under specific conditions, sodium can form diatomic molecules. So therefore, correct. There is a tendency, but the conditions are a little bit different from the normal conditions. Chlorine is anyway making a diatomic molecule because chlorine is existing as Cl. So A and D correct. If A and D options are correct, I have given you to choose as answer 4. Question number 31, answer is fourth one. Question number 31, answer is 4. Question number 32. First 7 ionization energies of element, capital X, are as follows. Right. So by looking at the values, I'm drawing the graph roughly in this way. 1, 2, 3, 4. When you consider the ionization energy values that they have given, roughly we can sketch a graph like this. And we have sudden increment. Ionization energy is 84,706, 13,300, 11,000, 7,460, 5,310, 3,380, 1,310 in this way. Okay. So when you analyze this ionization energy graph, I1 to I7, can't you tell me, students, what is the group actually? What is the group that element belongs to? You can tell that one. So you can see that when you analyze this one, this is the place where you can see the large energy gap. So that large energy gap is representing two energy levels, right? This electron belongs to a principal energy level, and these electrons also belong to another principal energy level. So therefore, it's representing the difference between two principal energy levels. Then you can tell these are the S2 electrons, S2. And what about these 4 electrons, P4? Therefore, we can tell that this is actually S2P4 valence configuration. S2P4 valence configuration. S2P4 valence configuration can be seen in group number 16. Right? See how easy these things are. Right? The correct statement about capital X, it belongs to the group number 16 of the periodic table. Yes. The minimum valency is 2. Yeah. In the second unit, we discuss about the valency. What are the group number 16 elements? Oxygen, sulfur, selenium, tellurium, polonium. These are the group number 16 elements. Their valency is 2. Main valence is 2. That is the minimum value. It can easily form X plus ion, X6 plus ions. No, students, it can't form positively charged ions. Normally, group number 16 elements are forming anions, O2 minus, S2 minus, selenium is C2 minus. So they are forming 2 minus anion because easily they can gain electrons rather than removing electrons. So here, X6 plus means removing electrons. So therefore, that is difficult. Huh? So it's not possible. It can only form anions but cannot form covalent compounds. It can only form anions, that's okay, but cannot form covalent compounds. That is wrong, because we know that many compounds are there. For example, H2O, oxygen is forming a covalent molecule. So therefore, that statement is completely wrong, right? So in the question number 32, simple A statement correct, B correct, C wrong, and D also wrong. So therefore, question number 32, answer is first one. Question number 32, answer is first one. Right. Question number 33. The correct statement regarding the emission spectrum of hydrogen is R. So it occurs when electrons are excited to high energy levels from low energy levels. Is that correct? Emission spectrum is obtained when the electrons are coming from high energy level to low energy. So they have given it occurs when the electrons are excited to high energy levels from low energy. Opposite, they have given the statement for the absorption spectrum. Wrong. First statement is wrong. Simple A is wrong. The energy transition when electrons falls from the fourth principal energy level to third, when the electrons falls from the third level to second level are equal. Let's see. Let's draw the hydrogen emission spectrum energy level diagram again. When you are answering for the hydrogen emission spectrum question, better you roughly draw the energy level diagram. Okay. Roughly you can draw that one in small. So I think here fourth principal energy level is right. The energy transitions when electron fall from the fourth principal energy level to third, fourth to third. This is equal to when the electrons is falling from the third energy level to the second. Students, these two are completely different two electrons of transitioning, right? 3 to 2, the gap, energy gap. They're asking when the energy transition, the electrons falls from uh, energy transition are not equal, right? So the energy gap, they are talking about the energy gap. Energy gaps are completely different. That's wrong, right? The frequency difference between the H alpha and H beta lines. So what is H alpha and H beta? Let's draw the line on. Let me consider from this side. You can draw the diagram for any direction, doesn't matter. Right. So students, you know that this line representing the H alpha and this line representing the H beta. So they're asking the frequency difference between the H alpha and H beta. Then H alpha is this one, H beta is this one. So the gap between these two will be this one, 4 to 3, this gap. Okay. Is equal to the frequency difference between the second and third lines found in the Lyman series. This is the second line and this is the third line. Gap between these two. Yes, both are same. Ne? Both are same. Second and third. That means, students, you can tell that first the gap between the energy gap between the first line and the second line in Balmer series equal to the gap between the second and third line in the Lyman series, right? So energy gap is actually proportional to the frequency. So therefore, we can apply that one for the frequency as well. So therefore, the C statement is also correct. The gap between Lyman and Balmer series is higher than the gap between Paschen and Balmer series. Yeah, that's correct, students, because actually for this direction, I told you that the frequency is increasing for this direction. For this direction, frequency is decreasing. So the gap between, when you draw the spectral line diagram also, between the Lyman and Balmer, energy gap is greater. That means frequency is greater. But when you go for the Paschen, bracket, fun, likewise, the energy level gaps are decreasing. Therefore, the frequency gaps are also decreasing. So therefore, this statement is correct. C and D both are correct. A statement is wrong. B also wrong. C correct and D also correct. So therefore, question number 33 answer is 3. Question number 33 answer is third one. Question number 34. The correct statement regarding the cathode rays. Its E over M value differs from one gas to another. Students, remember, I told you that E over M ratio value is a constant. 1.759 10 to the power 11 coulombs per kilogram. That's a constant value for any kind of a gas. Whatever the gas you use, whatever the metal that you are using as a cathode and anode, doesn't matter. E over M value is same. So therefore, we can say that. So this statement is wrong. Question number 34, simple A statement is wrong. Simple B, it is emitted perpendicular to the surface of the emission. Normally that's correct. Ne? We consider that cathode is in this way. So the perpendicular, yeah. So that's correct. So these are perpendicular to the surface. Yeah, that's correct. B correct. What about C? Since it create a momentum, it has a mass. Yeah. So that is actually an experiment conducted by J.J. Thomson. Can you remember what is the experiment? So he put some kind of a paddle wheel. So the paddle wheel started to rotate when the cathode rays are striking to the paddle wheel started to rotate. So and it started to rotate towards the anode. So therefore cathode rays can do a work. It has a momentum because it has a mass. So therefore it's correct. C statement is correct. D statement, electrons in an element are identical to cathode rays. Yeah, electrons are another than cathode rays. Correct. B, C, D statements correct. Question number 34. Answer is number 5. B, C, D statements are correct. Question number 34. Answer is number 5. Right. Let's move to the question number 35. Question number 35. The last electron filled into a certain atom according to the Aufbau principle has quantum number n equal 3 and n equal 2. Which of the following statement and statement is are true regarding that electron? Students, can you remember the Aufbau principle? Uh, Aufbau principle is explaining how the electrons are filling to the atomic orbitals. So using the Aufbau principle, we can obtain the electron filling order. Using the electron filling order, we can find out the electron configuration, right? So therefore, according to the Aufbau principle, so we can draw in this way, S5P. Right? We discuss about the Aufbau principle in this way. Right? 1s, 2s, 2p, 3s, 3p, 4s, 3d in this way. Okay, how about now? Students, can you hear me? Can you hear me now? Right. So now listen to this one. So they have given that the last electron fill into the certain atom has quantum number n equal 3 and L equal 2. So n equal 3 means third principal energy level, L equal 2 angular momentum quantum number, L equal 2 means d sub energy. So therefore third principal energy level d sub, right? Then we can say that uh, the electron is in d orbital. Yes, that's correct. The spin quantum number of that electron should be plus half. It's not correct. It can be plus half. We cannot tell that it should be plus half. It can be plus half or minus half. So therefore B statement is wrong. What about C? That electron can be removed when first ionization energy of the relevant to that atom is supplied. Remember students, we know that when we are arranging the configuration, when we write down the electron configuration, then it is 1s, 2s, 2p, 3s, 3p, 3d, 4s. Because we know that before 3d electron, 3d orbital field, 4s orbital is already filled, right? According to the Aufbau principle, before we fill the 3d orbital, 4s electron are filled. So therefore, when we arrange the configuration, so the valence configuration should be 3d4s. That means exactly the last electron is in the fourth principal energy level, S sub energy level. That means when you give the energy in order to remove the last electron, the electrons are removed from not from the D sub energy level, it is from the fourth principal energy level, S sub energy level, right? If you give the energy that is equal to the first ionization energy of that particular atom, then the electrons are removed from the S sub energy level for S orbital, not from the 3D orbital. Why? Even though the electrons are filled to the D orbitals, at last, when we write down the configuration, we rearrange the electron configuration in this way. So the electrons are removed. When the electrons are removed, it is going for the fourth principal energy level S sub energy because it is the exactly last one, right? Then this statement is actually wrong. Try to understand now. Carefully read the statements and try to understand. The electron can be removed when first ionization energy relevant to the atom is supplied. No. Right? In order to remove that electron, we have to give at least the third ionization. Because in the 4s, we know that 2 electrons are there. So therefore, we have to go for the third ionization energy, at least. The electron exists in the third principal energy. Yeah, that's correct. Right? So A, B, C, D, when you consider the statements, A, B, C, D statements, A correct, D correct, B and C are wrong. So therefore, question number 35, answer should be fourth one. Question number 35, answer should be fourth one. Right, okay. Now let's go for the question number 36. Which of the following statement are true regarding quantum numbers? The maximum number of electrons in an energy level is given by n squared. Is that correct? Remember, students, the maximum number of electrons in an energy level is given by 2n squared. Okay. Remember, the maximum number of electrons in energy level, maximum number of electrons is given by 2n squared. So therefore, the first statement is wrong, right? They have given A, B, C, D statements. Let's see. First statement is wrong. B, the number of electrons may present in the principal energy level is always equal to 2n squared. So the number of electrons that may present in the principal energy level is not always equal to 2n squared. So this 2n squared is maximum, right? Maximum is the 2n squared. So therefore the B statement is also wrong. C, the maximum number of electrons present in principal energy level is given by 2n squared. Yeah, so this is it. Correct. The maximum number of orbitals present in the principal energy level is equal to n squared. Yeah, that's correct. Remember, these are the total number of electrons. We know that in an orbital, there will be maximum 2 electrons. So in order to obtain the maximum number of orbitals, you have to divide this one by 2. Then you will have 2n squared divided by 2, n squared. So the maximum number of orbitals are n squared. Maximum number of electrons will be 2n squared. So C and D correct. Question number 36, answer is third one. Question number 36, answer is third one. (37) is also easy. Which of the following ions have the electron configuration of a noble gas? A, B, C, D. Cr3 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. So therefore 3d3. Copper 2 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Scandium 3 plus 1s2, 2s2, 2p6, 3s2, 3p6. Then we have gallium 3 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. So students, you can see that this is not a noble gas configuration. And this is also not a noble gas configuration. But scandium 3 plus, yeah, that is actually argon's configuration, right? So gallium 3 plus, no, that is also not a noble gas configuration. So the only noble gas configuration can be seen in scandium 3 plus. So therefore, only C, therefore option is number 5. Question number 37, answer is number 5. Question number 37, answer is number 5. Right. Question number 38 also related to the emission spectrum. Let's see quickly. Figure below shows the 3 situations A, B, C where an electron of hydrogen atom transfer from ground state to excited state and excited state to ground state. Which of the following statement is true regarding A, B, C? So first of all, let's write down. Let's draw the diagram they have given. Because in this diagram, emissions, absorptions, both are included, right? So therefore, we cannot specify this one as emission spectrum or absorption spectrum. Both emissions and absorptions are there. So for this direction, they have given that energy is increasing. So energy levels n equal infinity level, 4, 3, 2, 1. And they have given electron transition capital A from n equal to 1 to n equal to. Electron transition capital B from 2 to 1. This is n equal 1, n equal 2, n equal 3, n equal 4, and this is n equal infinity. So capital C electron transition is from n equal 1 to infinity. So this is C. Right, let's see what are the questions they have asked. What are the statements they have given? Wavelength of the energy released in the transition capital A is corresponding to the Lyman series. Yeah, that is okay. Wavelength, when you consider the wavelength, electron transition capital A, but it is an absorption. Even though it is absorption, we can consider that is the energy, the frequency or the wavelength, everything belongs to the Lyman series. Okay. So therefore, simple A statement. What they're asking here, true regarding ABC. But remember, students, wavelength of the energy release. Remember, this is not release energy, right? Low energy level to high energy level, energy is absorbed. So therefore, that release term is wrong. Okay. So therefore, simple A statement, the only error is the wavelength of energy release. In absorption, when the electrons are going from low energy level to high energy level, they are absorbing energy, not the releasing energy. So therefore, that is wrong. Okay. Again, we have a question that how that orbitals becoming 2. Now, for example, let's consider the second principal energy level n equal to. In the sub energy level, we know that the second principal energy level, we have S and P sub energy level. Okay. S sub energy level containing 1. And P sub energy level. How many electrons are there? 1, 2, 3, 4, 5, 6, 7, 8. So therefore, the total number of electrons, maximum number of electrons will be 2n squared. That means 2 into 2 squared. That means 8. Then how many orbitals are there? Orbitals will be 1, 2, 3, 4. So therefore, we can say that 4 means 2 squared. 4. Right? Number of orbitals will be n squared. Right? 2n squared divided by 2 means n squared. Right? So therefore, n squared is 4. You can apply this one for the even for the third principal energy level. In the third principal energy level, we have S sub energy level, P sub energy level, and D sub n equal 3. SPD. In the S sub energy level, we have 1 orbital, P sub energy level 3. In the D sub energy level, we have 5 orbitals. So when you consider the total number of electrons, 2n squared, that means 2 into 3 squared, there will be 18. You count the number of orbitals. Orbitals will be 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 3 squared. Right? Orbitals will be 3 squared, n squared. Right? Remember that maximum number of electrons in a particular principal energy level is 2n squared. Maximum number of orbitals in a particular principal energy level is n squared. Right? N squared and 2n squared. 2n squared. Right? Okay, now back to the question again, 38. An emission spectrum at transition capital A and absorption spectrum at capital transition B can be easily observed. No, students. Capital A is absorption, capital B is emission. Capital A is absorption because it's going for it's going for high energy level. Capital B is emission. But in the statement B, they have given the opposite thing, right? So therefore wrong. In the capital B, they have given opposite, wrong. Wavelength of the energy release in transition B corresponding to the Lyman series. N equal 2 to 1. Yes, definitely that is Lyman. C statement is correct. A wrong, B wrong. C statement is correct. D statement. Wavelength of the energy release in the transition C corresponding to the first ionization energy of hydrogen. Is that correct? Students, we know that ionization energy means, when you consider hydrogen gas, ionization energy means monopositive hydrogen gaseous cation is formed by removing 1 mole of electrons. So that electron is released. We know that the one and only electron in the hydrogen atom is containing in the first principal energy level. So this electron is going for the infinity level. So that's what meant by the ionization energy. Ionization energy means this electron is going for infinity energy level. Then the statement they have given, simple D, is also correct. Question number 38, answer is third one. C and D statements are correct. Therefore, answer is third. Question number 39. Which of the following statements is regarding properties of the atoms? Are they asking the correct one? Okay, correct statement. Which of the following correct statement regarding the properties of the atoms? In the simple D statements, yes, Diduli, you are correct. Wavelength of the energy release in transitions is corresponding to the first energy of hydrogen. That means here only in these four Yeah, in the question number 38, A statement is wrong, B is also wrong, C is correct, okay. But the D statement is, I gave you that is correct, but remember students, they have given the wavelength of the energy release. It's not release energy, it is absorbed energy. Ne? So therefore, this one also wrong. Okay. So question number 38, answer should be 5 then. I corrected your papers by considering the answer number 3. It's okay, fine. Let's see. So 1 mark will go here and there between the answer sheets. Okay. Yeah, visually correct. It's correct. Okay, right. So that is question number 38. Answer should be 5th. Then go for the question number 39. Which of the following statements is regarding properties of atoms? Covalent radius of carbon atom is less than the van der Waals radius. Students, we know that when we discuss about the atomic radius, we discuss about 3 types of atomic radius. So what are the 3 types of atomic radius? Number 1 is covalent radius. And the second type is van der Waals radius. Van der Waals radius. And third one is metallic radius. So when we consider these 3 types, we know that covalent radius is when they are forming covalent bonds. We are taking the distance between the 2 nuclei, and the half of the distance will be covalent radius, right? So that means D covalent radius is equal to half of this one. So this is covalent radius. Van der Waals radius means when the atoms are as much closer to each other, then we take the distance, and this is van der Waals radius, dO. And metallic radius is the perfect radius that we can measure, right? When we have the 2 atoms in this way, metallic radius is in this. This is the internuclear distance. So I told you that students, when you consider the exact radius of atom is almost equal to the metallic radius. But when you compare that one with the covalent radius is lesser than that. Van der Waals radius is greater than everything, right? Van der Waals radius is greater than everything because van der Waals radius means the atoms are closer to each other, but they are not actually intersecting, right? They are not actually forming bonds. They are not colliding. So therefore, we take the distance. Then covalent radius of carbon atom is less than its van der Waals radius. Answer number simple A statement is correct. Covalent radius is lesser. Simple B. According to Pauling scale, electronegativity of sodium atom is less than that of aluminium. Is that correct? We know that electronegativity is increasing from the period. Along the period, electronegativity is increasing, right? So therefore, sodium has the less value than aluminium. That's correct. Simple B is also correct. Simple C. Ionization energy of an atom is determined only by its nuclear charge. No. Ionization energy of an atom is depending on the atomic radius, then the electron configuration also. I told you that one. Electron configuration is also an affecting factor for the ionization energy. So therefore, simple C statement is wrong. Simple D. Second ionization is maximum for the elements in the group number 2. No, for the group number 1. So therefore, 39. Answer is A and B. Since A and B correct, answer is number 1. In question number 39, A and B correct, answer is number 1. Question number 40. Question number 40 is very easy. Of the following scientists who contributed in creating the periodic table, Mendeleev, Lothar Michael Faraday, and Avogadro. Michael Faraday and Avogadro didn't contribute for development of the periodic table, only Mendeleev and Lothar. So therefore, question number 40, answer is number 1. Okay, that's very easy. Question number 41. In a magnetic field, the accelerated electrons move towards the north pole, while in an electric field, they move towards the positive terminal. What do you think? In a magnetic field, then question number 41 to 50, we have two statements. You have to consider which statement is correct, and according to the given response, you have to choose the correct one, right? In a magnetic field, the accelerated electrons move towards the north pole. Can we tell like that? I told you that we can't tell whether it is moving to the north pole or south pole. They are going perpendicular to the magnetic field, right? While in an electric field, they move towards the positive terminal. Yeah, in the electric field, actually, they are moving to the positive terminal, but in magnetic field, we can't say that it is exactly moving to the north pole. It is actually going perpendicular to the magnetic field. Since accelerated electrons have a negative charge, they behave in the same way as negative particles. Yeah, that's correct. So negative particles means actually cathode rays, right? So therefore, since the accelerated electrons have the negative charge, they behave in the same way as negative particles. Beta rays, cathode rays, correct. So therefore, first statement is wrong, but the second statement is correct. Question number 41, answer is 4. Question number 41, answer is 4. Question number 42. The van der Waals radius of an element is smaller than the covalent radius. Just now we discussed. I told you that van der Waals radius is the greatest one. So therefore, in the question number 42, first statement is wrong. The covalent radius of an element is half of the internuclear distance at any instance. Remember, students, we can't tell that at any instance. We are measuring the covalent radius when they are making covalent bonds, right? If they are not making covalent bonds, can we take the internuclear distance and say this is covalent radius? No, that's not correct. Right? That is wrong. So at any instance, that term is wrong, right? We have to measure the internuclear distance when they are making a covalent in order to measure the covalent radius, right? So therefore, both the statements are wrong. Question number 42, answer is number 5. 43. First ionization energy of aluminium is higher than sodium. So first ionization energy graph, we discussed that one. When you consider sodium, magnesium, aluminium, this is the variation. Sodium, magnesium, aluminium. So according to this variation, sodium has the least value. So first energy of aluminium is higher than sodium, correct. Electronegativity of aluminium is higher than sodium. Yeah, that's also correct, because I told you that along a period, electronegativity is increasing. Since the electronegativity is increasing, aluminium has the greatest electronegativity value. But is that affecting to the first statement? Because we have option like this: true, but does not, but correctly explain the first statement. Is the second statement explaining the first one? Because of the, is that the because of electronegativity that ionization energy is greater? No, we can't compare like that. Aluminium has a great ionization energy because of the radius. The radius is lower. Aluminium's radius is lower. Therefore, it has a great ionization energy than sodium, not the electronegativity. So, second statement is correct, but it is not explaining the first one. Therefore, question number 43, answer is second one. In the question number 44, they have given about the electron configuration. 3d5 4s1 configuration is more stable than 3d4 4s2. It's correct, students, because we have discussed that chromium's electron configuration. We are expecting that chromium's electron configuration 24 should be 3d4 and 4s2. But we know that this is rearranging in order to obtain the greatest stability 3d5 4s1. Because 3d5, all the d orbitals containing one electron for each. And in s orbital also one electron. So therefore, we can see a symmetrical order. Therefore, 3d5 4s1 is stable than 3d4 4s2. So that statement is correct. The atomic orbitals are completely filled when possessing 3d5 4s1. Not completely filled, half filled. So therefore, the second statement is wrong. Question number 44. Answer is third one. For the question number 45, actually, I have given you two answers. I'll tell you the reason behind that. Okay. Electronegativity of sulfur is higher than that of nitrogen. Okay. Remember, students, I told you in the third unit also at the beginning, at the starting of the third unit, I told you that we have to remember the electronegativity table. Right. So at least for the second period, third period, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Okay. Remember, students, fluorine is the most electronegative atom. Therefore, its electronegativity is 4.0, 3.5, 3.0, 2.5, 2.0, 1.5, 1.0. Can you remember the pattern? The pattern is decreasing pattern. From right to left, 0.5 by 0.5, it is decreasing. Okay. And when you come from fluorine to chlorine, electronegativity value is decreasing by one value, 3.0. Oxygen to sulfur, 2.5. Then remember, I told you that you have to remember for phosphorus and hydrogen, both of them have same value according to the Pauling scale. Then from phosphorus to sodium, the values are decreasing by 0.3. 0.3. Then we can see that this is the way that at least you have to remember the electronegativity values of these elements. Okay, keep that in your mind. This is the pattern. Okay? From here to here, 0.3 by 0.3, the values are decreasing. From here to here, 0.5 by 0.5, the values are decreasing. Okay. So electronegativity of sulfur is higher than that of nitrogen. Is that correct? Nitrogen is 3.0, sulfur is 2.5. So therefore, nitrogen is the greatest one. So therefore, the first statement is wrong. Ability of an atom to pull electrons towards it is the electronegativity. Okay. Now, I have considered this statement is correct as well as wrong. The reason that I consider this statement as correct statement, students, yeah, electronegativity means ability to pull the electrons. That is the simple idea. But remember, we are pulling electrons from where? Where we are doing this one? Where the atoms are pulling electrons from the other atoms? When they are making chemical bonds. When they are chemically bonded, the ability to pull the electrons is known as the electronegativity. Actually, they haven't given the correct definition for the electronegativity. So that's why I consider wrong because of not having that bonded when the elements are bonded. They have to mention that when the elements are covalently bonded. So in an atom, ability to pull the electrons from the other atom, right? So simply we can tell that ability to pull the electrons from another atom is the electron. So therefore, I have given you 4 and 5, both are correct. Okay. If you consider second statement is correct, then the answer is number 4. If the both statements are correct, answer is number 5. I have given the answers for both the statements in the exam. Okay. Right. Mass of a neutron is greater than mass of electron. Students, you know that one definitely. Mass of a neutron is greater than mass of electron. What is the mass of electron? 9.107 10 to the power minus 31 kilogram. And neutron mass 1.627. I can't remember. 1.67227. Tell me what is the mass of neutron? minus 27 kilograms. What is the mass of a neutron? Put your answer in the chat box. I think 1.675, right? 1.675 10 to the power minus 27. Mass of a neutron. So therefore, anyway, mass of a neutron is greater than mass of electron. Cathode rays have wave property as well as particle property. Yeah, that's also correct. So both the statements are correct, but there is no connection between the statements, right? Cathode rays have wave properties as well as particle property. Is that the reason for having a greater mass of neutron than electron? So therefore, question number 46 answers second one. Okay. Question number 47. Nucleides are atomic species with definite number of protons and definite number of electrons. Remember, students, nucleides are definite number of protons and definite number of neutrons. Those are not the electrons. Okay. So therefore, first statement is wrong. Though hydrogen 1, hydrogen 1, hydrogen 1, are isotopes of the same element, those are not nucleides. Actually, they are nucleides. We can consider they have certain number of neutrons, different neutrons, and they have same number of protons. Doesn't matter, but they are certain. So if they have certain number of neutrons and protons, even though they are isotopes, we can consider they are nucleides. So therefore, both the statements are wrong. Question number 47. Answer is number 5. Question number 48. Two electrons in a certain atom do not possess identical set of quantum numbers. Yes, correct. So this is actually meant by, this is actually said by Pauli's exclusion principle, right? When an orbital, there are two electrons, they have different set of quantum numbers. So this is actually Pauli's exclusion principle. Electrons spinning in the same direction do not exist in an atom. Remember, students, there are electrons actually with the same spin. We can tell like this: electrons spinning in the same direction do not exist in a particular orbital. Then it is correct. In an atom, we have so many electrons in so many orbitals. So definitely they can have the same spin in an atom. Okay. So therefore, first statement is correct, second one is wrong. So therefore, 48 answer is third. The gap between two consecutive lines in the emission spectrum of hydrogen get decreased rapidly when the frequency of the spectral line get increased. Yeah. So according to the diagram that we drew, we know that for the Lyman series direction, we know that the gap between the lines are decreasing, right? So that is because of what? The energy rapidly. The gap between two consecutive lines in emission spectrum of hydrogen get decreased rapidly when the frequency of spectral line get increasing. Yeah, for that direction, frequencies increase. The distance between the energy level decreases with the increase of distance from the nucleus. Yeah, that is also correct. We know that when we go far away from the nucleus, energy gap is decreasing. So therefore, that's correct. So that's why when we are drawing the spectrum, we are denoting that the spectral line gap is decreasing in order to represent that energy gap is decreasing. So second statement is explaining the first one, right? So therefore 49 answer is second one, first one. Last one. The order of the electronegativity of elements boron, carbon, nitrogen, oxygen. boron, carbon, nitrogen, oxygen, fluorine in this way. Is that correct? Yeah, gradually increasing. That's correct. Electronegativity depends on the total number of electrons present in that atom. No, electronegativity is not depending on the total number of electrons. Okay. So for the electronegativity, there are many factors affecting, like hybridization. So we didn't discuss that one yet. Formal charge, oxidation number, surrounding atoms. So therefore, electronegativity is not depending on the total number of electrons in that atom. First statement is correct, second one is wrong. Therefore, question number 50 is correct. Right. Okay. Students, this is the end of the unit test paper discussion, atomic structure. Okay, right. I will upload the answers as a sheet to WhatsApp group. I will upload that one, and I will upload the recording also. Okay? So this is the thing. Whatever your marks doesn't matter for me, right? I need you to learn something from doing these papers. Especially, you have to manage the time. You have to remember all the theories, right? I think you got a nice experience by doing this paper. So therefore, for the unit number 2 and unit number 3 also, let's do these kind of 2 papers. So please learn these things properly. I believe that you identified your mistakes and correct those mistakes. Don't do those mistakes again. Okay. So that is the thing. That question number 38, there was a small issue. Therefore, sometimes your marks can be changed, right? It doesn't matter, only one MCQ. So therefore, it's okay. Right. Okay. So that's all about the discussion of the unit test. Right. Then students, I'm going to wind up the session. I will upload the recording with the answers to WhatsApp group. Next Saturday, you will have the remaining past paper MCQ discussion. I want to finish that one also. Okay, then let's meet on next Thursday. Until then, have fun. Bye bye.